So here we are, we've arrived at the final stage of aerobic cellular respiration, and we're ready to talk about chemiosmosis. So before we begin, let's talk about this title here, chemiosmosis. So chemi, to me, makes me think of like chemicals. And osmosis, we know that that describes the movement across, usually we're talking about water in osmosis, moving across some sort of a membrane. But in this case, it's chemiosmosis, so the chemicals are moving across a membrane. So you'll remember that the big deal about the electron transport chain was that we harnessed the energy released as electrons were shuttled from electron carrier to electron carrier, and that energy that was released was used to pump protons, pump hydrogen ions from the mitochondrial matrix to the intermembrane space. So as you can imagine, as our NADH is getting oxidized back to NAD+, we're getting a mass amount of hydrogens being pumped into the intermembrane space. And so what that's creating is a bit of a proton reservoir. So we have a high concentration of hydrogen ions, protons in the intermembrane space relative to the mitochondrial matrix. So there is a concentration gradient that develops. So the problem is that, well, actually it's not really a problem, this is how this works, is that the hydrogens ions are not permeable, or so that membrane is not permeable to the hydrogen ions. So they can't just simply diffuse through that phospholipid bilayer. The only way that they can get through is through a special proton channel, and that proton channel is called ATP synthase, sometimes shortened as ATPase, right? So you can sort of think of it, so as those protons are moving through ATPase, they have to squeeze through that one area, that one channel. In that process, the movement of those protons through that small channel is creating what we call proton motive force. So you can sort of think of it like, if you had just a hose with water flowing through it, but then somehow you took that hose and you've done what, a lot of kids will do when they're messing around, right? So here's your hose, water, but then, what might you do? You might sort of just kink it, right? I'm going to do a lousy job of this, by the way. And so what happens when you kink it? Well, you decrease the size, the radius of the hose, but what that does is it creates more force with the water. So in the same way, as we have hydrogens not diffusing through anywhere across that membrane, we have them funneling through a small area. That generates some force, which we call proton motive force. That is the force that is used, that is the energy that is used to take ADP molecules and phosphorylate them, producing ATP. This is what we mean by oxidative phosphorylation. Well, where did the oxidative piece come from? It came from the electron transport chain, which allowed all of these protons to be pumped into that intermembrane space, right? And then where's the phosphorylation bit? Well, it's happening as that proton motive force is used to add inorganic phosphates to ADP molecules to store that massive amount of energy. All right, so I still want to have a lot of this sort of down. So what I'm going to do is I'm gonna have this image here so we can refer to it if necessary, but we're gonna write some notes down. So first off, we know, well, what is happening? Those hydrogen ions are being shuttled from the matrix to the intermembrane space, and it's the electron transport chain that we have to thank for that. So as that's happening, well, what is happening next? Think about it. We know that that is creating a hydrogen ion reservoir. And then that hydrogen ion reservoir is helping to create a concentration gradient. Now we're specifically calling it an electrochemical gradient because it's not just chemical, it's electrical, because of course those protons have a charge. They are charged particles. Okay, so there we go. So what's happening is that in the intermembrane space, it's all becoming positively charged relative to the matrix. So, in other words, if we have a bunch of all the positive particles are moving out of the matrix, then we can say that it's not necessarily that the interior is negative, it's just negative relative to this intermembrane space. So that sets up, not just, a concentration gradient, but electrochemical gradient, and that's really just a potential difference or voltage, right? It's not unlike what happens in an electrical circuit where we have all the electrons at one end of the battery. Battery, all the electrons at one end of the battery, and then, what drives them is their attraction to the negative end, right? And that it creates that potential difference. So it's not unlike that. So other things to mention. Okay, so we know that there's the hydrogen ion concentration. So as I mentioned, well, why is it that these hydrogen ions aren't just sort of back into that mitochondrial matrix? Why do they just not flow back in there, right? Even though they've been pushed out. Well, the inner mitochondrial membrane is going to be impermeable to the hydrogen ions because we have that hydrophobic phospholipid bilayer, the tails of the phospholipid, which are those fatty acids, are not going to let those hydrogen ions through, not typically. So how do we overcome this? We have those ions traveling through ATPase, which is a specific enzyme geared towards allowing those hydrogen ions through. Okay, so the hydrogen ions are going to go through ATPase. Sometimes ATP synthase is for long, ATPase for short, and that is going to generate some usable energy, and we call that the proton motive force. Okay, so again, remember my little hose analogy over here, right? Just the forcing those ions in through only one, there's a buildup of them. They obviously want to, through diffusion, passive transport molecules want to move from areas of high concentration to low. The problem is they can't go through the membrane anywhere they want. They have to go through ATPase, but then there's like a backup, and that sort of like, not unlike the backup of water we would see in a hose if we were kinking it, that would create more force. Same sort of idea. Okay, so as our hydrogen ions are moving through ATP synthase, that is going to generate that proton motive force. And what is it being used to do? To phosphorylate our ADP into becoming ATP. So there is the last sort of bit. We're going to get lots of payoff from our phosphorylation here, the oxidative phosphorylation, because you'll remember in the last video that we talked about how for every NADH, we're going to be pumping 3 protons through the membrane, and for every FADH2, we're going to be pumping 2 hydrogens through the membrane. So, and we know that there's a one-to-one relationship between the proton and the ATP produced, right? So that's going to generate a lot more ATP than we saw in substrate level phosphorylation during the Krebs cycle and in glycolysis. So that is it, folks. That is chemiosmosis. Not much to say here. Yeah, that's it. So as always, feel free to reach out to me with any questions, or if there's anything that you feel I might have not made clear enough, just reach out via Google Classroom and let me know, and we'll work to sort it out.